Hello, Curtis.
Hello.
How was the exam?
Wasn't too bad.
Other again?
It wasn't too bad. It was pretty good.
Good. Give me a few minutes and set this up. Where is Gordon? He's usually here.
I'm not sure. I talked to him earlier. He said he was here. Yeah.
Here he is. How was the exam going?
Okay. Yes.
Harder than last time? Was it expected? But this time you cannot complain, right? Because this was take home last time.
Yeah, I knew it was going to be hard, so there were no surprises.
Last time you said that you were expecting, or it was, you say, I don't know what you exactly you had said. Think so? So I'm not going to have any homework today. The next homework will be posted on Friday. Today, what I want to do is that because there was a test, I had jumped a small part of the Green's function, so I'll cover that. And, on Friday, we will start something new. And homework will be posted then. So no homework for now. There is a midterm is over, so whenever after the homework is posted, so there's a final exam. And I checked in the final exam, or no, I think I told you guys before also, right? Some December 11, which is Friday. But even though there is a time, the exam will be take home. So will be posted early in the week, probably even 1 week early. Posted early, due by, let's say, due by 4:45 p.m. Okay, I think that's all. And we won't have a class on Wednesday because it's a holiday. And remember, there are only 3 weeks remaining, 3 weeks of classes remaining. There's this week, next week, and after Thanksgiving, there is one more week. So this week we lose 1 class. So there's about 2 weeks plus. So about 6-7 lectures after today. That's all information. Okay, so we talked about Green's function in the presence of a material, and somewhere in between, it was necessary to interpret what is a Green's function when there is no material at all. And I had skipped that. I only gave the indication that this will actually give an answer by setting it to be 0. But it's good to start from the scratch and do that separately. It follows pretty much the same thing, but since it is so important, I feel it should be done in a relaxed manner with rushing through. So this is called free Green's function. So free Green's function is a Green's function when the material properties are just the vacuum property, and our Maxwell's equation are, so we have divergence of electric field is equal to charge density, no material, so there is no divergence of the polarization. And across the curl of the electric field is actually 0 in electrostatics, which implies that the electric field can be written as a negative gradient of an electric potential, which gives us the Poisson equation. So this is, so substitute this in there. So we have L dotted with epsilon naught. Right. And in general, this could be a position dependent quantity, and that's what we have been working on. But in the simpler scenario, when this is vacuum, this can come out. So we simply have del square, right? Because it's a constant. It's del square epsilon naught phi of r is equal to if rho was equal to 0, that's called a Laplacian. So just for your information, minus del square of f is equal to 0. This is called this differential equation is called a Laplacian. That's the name of the differential equation. It's a very well studied object. And if you have the way we have it, so that's epsilon naught phi is equal to rho. This is called the Poisson equation. I think I'm pronouncing it right, Poisson. So I think the French word probably. Okay. So these are standard differential equations. So Laplacian is the homogeneous version of the Poisson equation. We found that whenever we have an inhomogeneous differential equation, we can write the Green's function for it. So we construct the Green's function as the Laplacian operator. So this is, by the way, this is called the Laplacian operator. That's some terminology. Laplacian operator. We have been consistently using this all through, but I didn't bother to stress that these are the names associated with it. Instead of the electric potential due to the whole charge distribution, we talk about a single point charge in there, and that's called the Green's function. G r, r prime. That's equal to so notice if you have a point charge, so there will be a Q sitting in front of it. So Green's function in this sense is is the electric potential due to a unit point charge. We know the solution immediately. We don't even have to actually work it out. So we know the solution. Right? So solution is, we're going to find another form of the solution, but we do know the solution of this, and that is epsilon naught. So G of R comma R prime is actually equal to 1 over 4 pi epsilon naught times 1 over R minus R prime. It is Q over R minus R prime if it was a point charge, but since Q is 1, so that's your Green's function. But we want to find another form of the solution, and which of course has to be exactly the same, so there will be an identity associated with that. We notice that if there is a planar symmetry, then we can separate out x and y. So x r is equal to xi plus yj plus zk. So it's a zz hat instead of k, because I use k for the Fourier variables also. This we said was r perp. Right. So this r perp. R perp is the component of the vector in the xy plane, and the Fourier transform of this quantity is k, which will be kx in the x hat direction plus ky in the y hat direction plus kz in the z hat direction. And again, this is k perp. That's your vector k perp. In terms of this, we showed that epsilon naught times the Green's function has the following representation. It's g2 k perp over 2 pi whole square. This is two integrals, dkx and dky, right? There's an integral over x and there's an integral over y, or kx and ky. And this is exponential of I k perp dotted with r perp. Like in fact, this was r minus r prime, right? R perp minus r perp prime. And whatever was left out was what we called the reduced Green's function. And since this can depend on k perp, let me put a dot there and write this depends on k perp. This just means that it depends on k perp. We have used the same notation for the Green's function in the presence of a material also. So let's, since we don't have any material, let's call this G naught. Right? That's what is meant by free Green's function. It's a special Green's function, so we'll call it G naught. So the other Green's function that presence of a material is G. This is G naught, and this is G naught. And the differential equation obeyed by T naught is second derivative with respect to z square plus k perp square, sorry, minus k perp square, and that is an overall negative sign, and then that is g of z comma z prime k perp, and that is an epsilon naught also. No, epsilon naught, that's equal to delta of z minus z prime. So that was our Green's function. the same boundary conditions work out. We can do the integral with respect to z. So we are interested in z less than z prime and z greater than z prime. So the differential equations we have is let me put everything in a single line. So this equation reads minus k perp square times g0, g0, z comma z prime is equal to 0 if z was less than z prime. And no restriction on z and z prime. It could be anywhere in the whole space. There is no material. I want to write this. Yeah. And we have the same equation if z prime was less than z. So again, there is a line, straight line on z and z prime. It's possible that there is z here. So that's your observation point, that's your z prime, or it could be the opposite. That's only two possibilities, right? Either the observer is on the right side of the source, or the observer is on the left side of the source. For these two regions, these are homogeneous differential equation. We know the solution immediately. So 0 z comma z prime has a solution, right? A times e raised to minus. So notice this is equal to 0. So these are not harmonic oscillators. This is hyperbolic oscillator if you want. So this is k perp times z plus p times k perp times z. This is for, let's say, z less than z prime. And there is another set of solution, e raised to minus k perp z plus d times e raised to plus k perp times z. This is for z prime less than z. It is convenient to look for solutions which are 0 at minus infinity and plus infinity. So what are the boundary conditions we want to look for? So that's our solution. And what are the boundary conditions? So boundary conditions are boundary conditions will be that the first would be that the Green's function at z equal to, as z tends to infinity, irrespective of where z prime is, that should be equal to 0. And why do you impose that boundary condition? Primarily based on the fact that this is going to be the electric potential due to a point charge, so you want it to be 0. In general, as a mathematical problem, this doesn't have to be there. So in principle, Green's function, there are various Green's function you can construct based on what kind of boundary conditions you impose on it. So Green's function has a freedom associated with that boundary condition. We also want z tending to minus infinity to be equal to 0. So that's the second boundary condition. And we also showed that there are continuity. Is what is called continuity equations, conditions if you want. And this is imposed by the equation itself. This is not that we are choosing this. This can be derived from the differential equation. And this comes out to be derivative of Green's function itself at z equal to z prime. So g of z prime plus delta, comma, z prime is entity of z prime minus delta, comma, z prime. So this is z equal to z prime plus delta. Has to be equal to 0, so it's continuous. Again, notice what we're doing. So that is z prime here. And this point could be z equal to z prime plus delta. So you approach from the right side and you approach from the left hand side. So that's the continuity conditions in that sense. And they need not be the same, but we impose that, or it's not that we impose this equation imposes that the Green's function has to be continuous, and its derivative, the same thing for the derivative. So this is first you evaluate z comma z prime, and then you evaluate it at z equal to z prime plus delta. So that's because when you integrate with z, there is a -1 that goes on to the other side. So that's a discontinuity in the derivative. We explicitly did this in the case of a material, and the same thing goes through here. And that's equal to -1. Why -1? Because when I integrate, there is this -1 which I take from to the right. So that's your 4 boundary conditions, and we can see. So let's call this 3 and 4, right, instead of 2 and that we have. Don't have any redundancy in the labels. So surely 1 immediately implies that at z equal to infinity, this anyway goes to 0, so b has to be equal to 0. Why? Because this anyway goes to 0. This seems to diverge at z tends to infinity, so that cannot be. Okay, so that's b is equal to 0. Second one imposes that at z equal to minus infinity, it should be 0. That requires that c has to be 1. Right. So, and that implies that G now has a simpler structure. Oh, all this, I keep forgetting that this was, we started calling this G naught, right? Friedmann's G naught. So G naught z comma z prime k per is equal to simpler form. So that is a times exponential of minus k per z, and otherwise it is d times exponential of plus k per z. So only 2 coefficients left. So this is when z is less than z prime, and this is when z prime is less than z. And this never, even though exponential, at least from one side, blows up, this requirement makes sure that that is low. Take the derivative so that we can use this boundary condition. So dg naught over dz. That's equal to minus k per a times exponential of z, and this is plus k per d exponential of plus k per z. And again, one is for z less than z prime, and the other is for z prime less than z. You guys surely did these things for your test also. It's a good exercise. Use the boundary conditions here. So 3 implies that, so notice z prime plus delta. Plus delta means I have, so z prime, z is greater than z prime, so z has to be greater than z prime if I have to. So if it is Z prime plus delta, I'm on the right hand side, so it is surely great. So that's D times exponential of plus k per times Z prime plus delta. But we have to take the limit delta tends to 0, so this can go away right away. Minus of A times exponential of minus k per Z prime minus delta. That's equal to 0. Again, delta can be taken to, you can take the limit right away there. Fourth one similarly implies, so derivatives are down here, that's minus, again, Z prime plus delta is the D term, that's k per D e raised to k per Z prime plus delta minus of minus k per, so that makes it a plus k per A exponential of minus k per Z prime minus delta has to be equal to minus 1. Take the limit delta tends to 0. This is the equation D times exponential of k per Z prime minus A times exponential of k per Z prime is equal to 0. Divide out by k per, so that I can write E of k per Z prime plus A times exponential k per Z prime is equal to minus 1 over k per. That's two linear, the linear set of equation, two unknowns, so we can get D to be equal to. So as a denominator, which is got by multiplying the coefficients in this diagonal sense, exponential of k per Z prime times exponential of minus k per Z prime. This multiplied by this, and then subtract it, but then you add up, right, because this is negative sign. And again, k per Z prime exponential of minus k per Z prime. But these terms cancel out, right? The exponentials cancel out to give you a 1. This also gives you a 1, so 1 plus 1 is 2. And the numerator is simply put this coefficients in there, so that's 0 times exponential of minus k per Z, and minus and a minus, that's plus 1 over k per times exponential of minus k per Z prime. If I got that right. So that's 0, that is denominator is 2, so that's equal to 1 over 2k per times exponential of minus k per Z prime. Similarly, A would be equal to, denominator is simple now, so it's just 2, and that's minus 1 over k per, this times minus, so it's exponential of k per Z prime, and minus 0, it's minus of exponential of k per Z prime times 0. Which is the same as what do you look at me? Did I mess up? Mess up.
I just saw that the generic system of equations way
Again?
I just solved it like the generic trivial
Yeah, that should be okay. But do you get the same equations?
Yeah, but if you would solve it right now, then A wouldn't be negative. Right, because you could like subtract.
Yeah.
Or no, A would still be negative. Anyway. It should be. So the equations are wrong, is that what you're saying?
Yeah, probably. Okay, so again, so this is continuity condition. So that's G is A exponential Z. It cannot, so it's on the left hand side, right? That's correct. So this is D. It can. Oh, this is wrong, right? I wrote it opposite, is it?
I think you did.
Yeah, I wrote the opposite, right? Yeah. I think, right from the beginning I said wrong. This is Z less than Z prime, correct? When Z is less than Z prime, so Z can be large. So at minus infinity, like Z cannot be plus infinity for this, right? So Z has to be minus infinity. So at Z equal to minus infinity, this diverges, this is okay. So it is A is equal to 0 and B survives. Is that clear, Gordon? Right? So the mistake I made was that I used the condition 1 to imply that, oh, Z tends to infinity, but Z tends to infinity has to be done on 2, right? Because Z cannot be infinity in the first equation to begin with, because Z is less than Z prime. So this implies, so 1 does not imply B equal to 0. Instead, it implies that D is equal to 0. Okay. Curtis, is that clear?
Yeah, I think so.
Yeah. Okay. So this, so let me not erase this. So this is D equal to 0. Okay. And this is not C. This will imply that A is equal to 0. Very sorry about that.
And then,
So then all our equations will change.
so all the D's would be negative.
Yeah, so this will now be A is 0, so this is plus, right? So this will be plus. And A becomes B, right? So this is B. Okay. And D becomes C. And the sign changes. Very sorry. Very bad. I should have caught it right there. Okay. So this becomes a positive sign. I'm not erasing so that you guys can follow. And this is positive. And this is B. This is negative. D is C. And this is negative. So this will now be, I think from this state I can just erase this, it's easier. Is that okay?
Yeah.
So I'm going to restart this thing. Very sorry. So this now becomes C times exponential of minus K per Z prime, right? And I've set delta tends to 0. So C has to equal this, so it's minus of B times exponential of k per c prime has to be equal to 0. We're working with C and B. All right, these two are the solutions. And the other equation is minus k per c exponential of minus k per c prime minus of k per b exponential of k per c prime has to be equal to -1. Rewrite this again. So this is c e raised to minus k per c prime is b exponential of k per c prime is equal to 0. Multiply by a minus sign divided by k per. So this is minus k per c prime plus b exponential of k per c prime, and that's equal to 1 over k per. No negative signs at this stage. Again, do find c and b. So denominator will be this times this is 1, this times this is 1. So that's 2, 1 plus 1. And this is 0 times exponential of k per c prime. So 0 times this. And plus 1 over k per times k per c prime. So that's equal to 1 over 2 k per exponential k per c prime. And b similarly is, again, that is a factor of 2, 1 plus 1, and this time it is 1 over k per times exponential of minus k per c prime, and the second one is 0. So both comes out positive this time, probably correct. K per c prime. Substitute this in the expression for G naught. You have B, that is 1 over 2k per times exponential of minus k per c prime, and that is already a plus k per z. So this is for z less than z prime. And the other solution is 1 over k per c, right? C is exponential of k per c prime and minus k per c prime plus z. This can be, it is, the minus sign comes with the greater one, right? Z prime is greater in this case, so that minus term comes with that. And in this case, minus comes with the greater than, that is c. So that means this is always equal to 1 over 2k per. So I can combine these two as minus k per times z and z prime. So the magnitude when z is greater than z prime takes care of that fact. Okay, so that's our solution for the reduced Green's function, in the sense it's the z dependence, but we have to go back to our Green's function. Okay, again, sorry about this error. Okay, so if I recollect what we have done, so there is something to learn here. It is, we have epsilon naught. So first of all, we know that the Green's function very clearly is the solution for a point charge. No doubt that this is this. As a solution, right? There's no doubt that's going to change. But now we have a new way of writing this, and that is that r comma r prime is also equal to, as an integral, d2k per, two integrals to be done, as an integral on x and kx and ky, I k per dotted with r per minus r per prime times 1 over epsilon naught times the Green's function, which we found, right? We found the answer to that, and that's this. This integral need not be easily doable. In this case, it is actually doable, but this means that these two have to be the same. That means we have an identity that 1 over 4 pi epsilon naught times 1 over r minus r prime. Remember, r minus r prime is nothing but, if you want to explicitly see this, 1 over 4 pi epsilon naught over square root, right? Square root of the per components. So it is r per minus r per prime square plus z minus z prime square. There's an x minus x prime square plus y minus y prime square sitting in there. So that's this quantity. Right? That's equal to this. So let me write that expression also. This is nothing but, so this is the total vector, but this is the x and y removed out of it. So squared plus z minus z prime squared is equal to d2k per over 2 pi whole square times exponential times 1 over epsilon naught 1 over 2k per times exponential minus k per z minus z prime. Couple of interpretations. One interpretation is that this is nothing but a Fourier transform, right? The Fourier transform of a 1 over r function is nothing but Fourier transform in 2 dimensions, right? X and y is nothing but exponential of minus k over 2k. That's one way of interpreting it. The second is that this is an identity. Whether you know how to do this integral or not, even if it is not doable, this has to be exactly equal. So this is an integral representation. So this is an integral representation, even if this integral is not doable. But this integral can be done just for information. Integral representation of the free Green's function. That means to say that you don't evaluate this, even though you know how to evaluate it, you don't evaluate it because this representation is more powerful. Like often you can derive identities associated with this. For example, what if there are two such functions, how does it go about? So that's the scenario, which means that whenever you see the structure, you should be able to say that, oh, this is a free Green's function. Like whenever we see this, now we have enough experience that, oh, this is a point charge. That's a Green's function, or that's electric potential due to a point charge. With sufficient practice, even when you see this, you should be able to say that, oh, this is the electric potential due to a point charge, and proceed accordingly. So that's what I wanted to do today. And I'll stop here. And we'll start something different on Friday. I haven't decided exactly what either I will do material properties or I will try to do the stress tensor method of electromagnetism. So the second. That's all. Thank you.
So G is just solving basically the homogeneous part of the differential equation for the potential. Right?
G or
The G, like capital G.
not the homogeneous, inhomogeneous.
So homogeneous isn't when it's set equal to 0?
Homogeneous is when you set it equal to 0. So Green's function is the inhomogeneous part.
Okay.
So the point is that if you know the homogeneous solution, like assuming that you know when rho equal to 0, how do you calculate the rho not equal to 0? And the requirement for that is that you need at least one solution. You just have to guess it. There is no standard way of doing it. So Green's function becomes a sort of a standard way in the sense, instead of putting the rho, you put delta function. Once you know the Green's function, then you know everything. But it is requiring that the homogeneous solutions are known. Notice what we're doing, we're converting it into a homogeneous solution.
Right.
But using these two homogeneous solutions, we are actually getting an inhomogeneous solution. It's one small piece there, right? It's only one tiny r equal to r prime, but that makes it inhomogeneous.
Right. Yeah, that makes sense. Yeah, I was trying to think of it as like you're solving basically for the potential, but like in the absence of a charge, 0, but I wasn't thinking of it from like the differential equation standpoint. So then it makes sense to me that like, oh, how does this make sense? If you take the charge out, how does the math still work? But no, it makes a lot more sense.
So you find the solution in two different places, but then patch it. Right. Where the charge is, there has to be some conditions. Yeah. But then if you know point charge, you know everything. Right? Because then it's any distribution can be part of it. Yes. So that's the idea of Green's function. One, if you know the solutions for homogeneous equation, you can find the solutions for inhomogeneous. Any inhomogeneous. But it has to be one. I mean, to get this, see that this played a key role, right? The boundary conditions or the continuity conditions play a key role. Those are easy to deal with only in one-dimensional scenario. I'm not saying that it cannot be done. Like Green's theorem is very strong. You can do this a lot, but then it becomes geometric. In higher dimensions, it becomes geometric. Like algebraically, you can do this only in one dimension. Or conveniently, you can do it in one dimension.
It has to come out the same way, so it works out nowadays, but not necessarily. Okay. Yeah, that makes a lot more sense now. I guess
Yeah.
yeah,
Good. These sort of simple, it's not a trick. Once you know the what is that? What's the right word? The theme, right? The theme, then it makes more sense. Good. Okay.
in the diffy